Count the paths, difficulty medium. We're given a directed acyclic graph, a DAG, with V nodes from 0 to V minus 1 and a list of directed edges. We need to count the total number of distinct paths from a given start node to a destination node. Each edge is represented as edges at index I equals U, V, indicating a directed edge from U to V. So that is this. And actually, here's the whole method that we're given as a template. A method called count paths. The edges come in like this as a 2D array. So an array of two element, as an array of two element edges, from and to. The number of vertices, and that is the start node, and that is the end node. All right, what else can we look at over here? Example, so the edges come in like this. An array of arrays. So these are all edges. 0, 1, 0, 3, 2, 0, 2, 1, and 1, 3. Vertex count is 4, source is 2, destination is 3. How many paths are there? Well, we can go 2, 0, 3, we can go 2, 0, 1, 3, we can go 2, 1, 3, so that's a total of 3. So that's the idea. Constraints, vertices, so can be up to 1,000. Number of edges would be on the order of 500,000 or so. And that's kind of a lot. Expected complexities, V plus E, auxiliary space, V plus E, that's fine. Topic tags, yeah, that looks good. Dynamic programming, DFS, and of course graph, data structures, algorithms. Well, there would be other ways to do this as well. I don't know. But that is the way we're going to approach it. So what can we say about this? Well, it is a directed acyclic graph. That part is important. There's no cycles. So what we're going to do here is going to work. If there were cycles, it's not going to work. We are going to use depth first search. We're going to use memoization, which is a top-down dynamic programming technique. It's a recursive technique, and DFS is also a recursive technique. So the memoization will help with efficiency here. All right. What have we got here as far as data structures? I'm going to scoot this over. We've got a hash map. That's the memoization table. We'll talk about that more in a minute. This is a list of lists. Well, the way this is coming in as an array of arrays, it's not really that efficient as far as being able to do a quick lookup. Like, is there an edge from this node to this node? If we put it in a list of lists, basically an adjacency list implementation, then it is easy to do that lookup. So that's what we're going to do. How do we start here? We're going to initialize the adjacency list and just put an empty adjacency list in for each vertex. Then we're going to iterate through all the edges and each 2-element array in the edge array has a from and a to, and we're gonna put that in the adjacency list. So we do a get. We're gonna get the list for the from node, and we're gonna add the to node. So anytime we want to know if there's a directed edge from one node to another node, we look up the list in the adjacency list, and then we look, in the adjacency list, see if the other node is there. That was probably an over-explanation. And then depth first search. We're going to do a depth first search. All right, how is the depth first search going to work? Well, we're going to start it with the source and the destination. Now, if the current node and the end node that we pass into DFS, if those are the same, that's our base case, and we return 1. Okay, memoization. Which one do I want to look at first? If we've already calculated the number of paths from current to end, then we're just going to look it up right here. We're not going to recompute it. Okay? And then we're going to return it. If we haven't computed it, then we're going to compute it. This is the recursive step. We're going to iterate through all the neighbors of current, that is, everything that's in the adjacency list. We're going to recursively call DFS for each neighbor, and we're going to sum up the returned path counts. So that'll give us the number of paths from current to end, and then we're going to memoize that result and return the path count. What else? I think that's it. I think that's it. But let's try and submit it. See what happens. I'm going to scoot this over because the result actually shows up over here. You can't see the submit button now, but trust me, I just clicked it. Okay. That's it, please. Well, let's see. Time taken. I guess, yeah, like LeetCode tells you, how your score compares to other people's scores. Could be good or bad, I suppose. But yeah, please, like the video, subscribe. You'll get notifications. I try to put one of these up every weekday. And see you next time.